Okay, so I am going to give the Chinese remainder theorem today. I'm going to apply it to this system of congruences here. So we've got n is congruent to 32 mod 83, n is congruent to 70 mod 110, and n is congruent to 3 mod 27. Now in the previous video, we learned how to solve like one congruence equation like this. Now here we're going to solve three congruence relations simultaneously. The solution to this problem and the problem itself, as usual, I'm kind of sucking all of the soul out of this problem and just giving the abstract math problem. Reading the book about how this was stated in terms of farmers selling rice, three farmers selling rice in different locations. So it was given by Jiushao. In a book called A Mathematical Treatise in 9 chapters, and he calls this the tie-in rule. Okay, and so that's what we're going to call it. We call it the Chinese remainder theorem now. Okay, so what we're going to do is I'm going to walk you through how to solve a system of congruences like this. In some ways, I'm going to be a little more abstract, but I'm always going to come concretely back to this problem. One, I think it's just easier to understand, and two, that's how it was done, right? There wasn't, necessarily a unique formula given or anything like that, and we're not really going to get a formula, anyways. Okay, so there's several observations that we need to make. Again, we're going to assume that when we're solving a system of congruences like this, that the moduli, that is these numbers there, that they are pairwise relatively prime. So in other words, if you pick any two factors, any two moduli and compare them, their GCD is going to be 1. So they are pairwise relatively prime, meaning if you pick any two of them and compute the GCD, it's going to be 1. Or equivalently, none of them have prime factors in common. Okay, that's the first assumption that we're going to make here. And you can see how he also covers a case where that's not the case. He also covers a situation where that's not the case. And you can see in the previous video that I made about what's going, you can see in the previous video that I made on solving a recurrence relation about, I told you that the right-hand side here needs to be a multiple of the GCD of the two numbers, so you can see how maybe that might expand to a system of congruences. Anyways, I'm not going to talk about that anymore. I'm going to look at but he was able to do that. So I'm going to look at the more specific case of where we have moduli here that are all pairwise relatively prime. Okay, that's good. So what I want to do is just go over a couple of things here. So the first thing that we're going to do is we're going to make a number m. Let me write this in purple. M is going to be the product of the 3 moduli. So m1 times m2 times m3. Okay, or with these specific numbers, it's 83 times 110 times 27, and this is 246,510. It's 246,510. Okay, now the first thing that we need to understand is that whenever we have a solution to this system, it's not going to be a unique solution, because all we know, all we're requiring about n is just something about the remainder. I want, when I do n divided by 83, I want the remainder to be 32. When I do n divided by 110, I want the remainder to be 7. And when I want n divided by 27, I want the remainder to be 3. So, if you just look at this equation right here, 60 would be one solution to this. 30 would be one solution to this, because 30 divided by 27, the remainder is 3. But then if you add to that 27, 57 is also going to be a solution. So there's not going to be a unique solution. So we want to sort of sort of add a side condition, very similar to what we did in the system of equations, just the system of linear equations. We want to kind of add a side condition to get the best solution. And here, the best solution is going to be the smallest positive solution to this system of equations right here. So I want the smallest positive solutions to this system of equations right here. If I can get the smallest possible solution, then what I want to be able to say is that any other solution I can get just from that solution in some sense. Okay, so here's how I'm going to do that. I want to make an observation. If N1 and N2 are solutions, if N1 and N2 are solutions, then they are congruent mod M. If N1 and N2 are solutions, then they are congruent mod M. Okay, so why is that? So remember, an equivalent way to say that two numbers are congruent modulo a number like this, okay, is that their difference is a multiple of n. Okay, so N1. So why is this true? Let me prove this. So proof. So we're going to let N1 and N2 be solutions mod M. Or we're going to let N1 and N2 be solutions to this congruence, this system of congruences. I want to show that they are equivalent mod M. Okay, so first of all, notice that N1 and N2 are congruent mod 83, mod 110, and mod 27, right? Because N1 is equal to 32 mod 83, and N2 is also equal to 32 mod 83. So N1 and N2 are congruent mod 83. So we know that N1, like I was just saying, whenever we know that two numbers are congruent modulo a modulus, then their difference is a multiple of that modulus. So N1 minus N2 is equal to, I'm going to say, K1 times 83. Or let me say a little more generically, K1 times M1. Okay, and similarly, N1 minus N2 is equal to K2 M2, or K2 times 110. And finally, N1 minus N2 is equal to K3 times M3. Okay, so what this means is that M1 divides N1 minus N2. It's a divisor of N1 minus N2. In other words, if you do N1 minus N2, you get, if you do N1 minus N1 minus N2 divided by little m1, you get K1, an integer. And similar for N1 minus N2, M2 divides N1 minus N2, and M3 divides N1 minus N2. So M1, M2, and M3 all divide N1 minus N2. Now, in general, if we have that, what we want to conclude then is that M1 times M2 times M3, we want to conclude that this divides N1 minus N2. That's what we want to conclude. In general, if we only know this information here, this is not going to be true. However, since M1 and M2 and M3 are relatively prime, this is going to be true. Okay, and that's because if you look at the prime factors for M1, M2, M3, they're going to have no prime factors in common. Okay, so M1, M2, and M3 are going to have no prime factors in common. So you're going to have some prime factors from M1 that are going to be a part of the prime factorization for N1 minus N2. You have prime factors for M2 that are going to be part of the prime factorization for N1 minus N2, and you have some prime factor. The prime factorization of M3 are also going to be part of the prime factorization for N1 minus N2. But since there are no prime factors in common, like the prime factors for M1 are not in the prime factorization for M2 or M3, the prime factorization for M2 is not in the prime factorization for M1 or M3, and the prime factors for M3 are not in the factorization for M1 and M1 or M2. What this means then is that each set of prime factors is going to divide n1 minus n2. And you're not going to have a situation where you have a prime factor here and a prime factor here, and so there, maybe you have a prime factor here and a common prime factor here. That would divide n1 minus n2, but then maybe n1 minus n2 doesn't have that square as a fraction, as a prime factor. Okay, so let me just do a little side note here to explain what I mean, because I can tell from the looks on your faces. I know you're not actually, I can't actually see your face, but I could tell through the internet and through time by the looks on your face what I just said there might not have made the most sense. Okay, so let's say I'm going to illustrate what happens when we have not relatively prime. So let's say I know m1 is equal to 2 times 3, and let's say I know m2 is equal to 2 times 5, and let's say I know m3 is equal to 7, and let's say n1 minus n2, I should have done this example before. Sorry, there's a noise happening. Oh my gosh. Well,
may I have your attention, please?
There's either a fire alarm
May I have
or
your attention,
the
please?
test.
There has been a fire emergency
Well,
reported in the building.
There's been a fire alarm.
Evacuate the building.
So I'm going to keep this going, and then if there's a fire, we'll get to see it on camera. If not, I'm going to come back and do this. Okay, so it was a fire drill. Anyway, so here I am back. Now, n1 minus n2, let's just say, what if n1 minus n2 is equal to 2 times 3 times 5 times 7? Okay, then m1 is going to divide this because 2 times 3 divides it. m2 is going to divide it because we have 2 times 5, and m3 is going to divide it because we have this 7. But notice that the product m1 times n2, m1 times m2 times m3 will not divide this, because when we do that product, we're going to have two 2's in the prime factorization, which we don't have over here, right? So if the only information that we have is m1 divides this, m2 divides that, and m3 divides that, then we know that we do not know necessarily that their product is going to divide that. However, in our case here, we are assuming that m1 and m2 and m3 are relatively prime. So in other words, you don't have this situation where you have an m1 and an m2 with the same common primes in their factorization. Okay, so therefore, m1 times m2 times m3 divides n1 minus n2. Well, what is m? M is just a product. This is m. m1 times m2 times m3, that's equal to m. So m divides n1 minus n2, but that's just equivalent to saying that n1 and n2 are equivalent modulo m, or congruent modulo m. Okay, so if you have two different solutions to this, they're going to be congruent modulo m. So then what we're going to do is we're going to find one solution to this system of equations, or this system of congruences, and then we're going to subtract off m as many times as we can to get the smallest positive answer. We're going to subtract off m as many times as we can to get the smallest positive answer. And then any other solution is going to be just that plus a multiple of m. It's going to be that plus a multiple of m. Okay, and again, you can see analogies here like we saw before with systems of equations, with solving homogeneous equations and non-homogeneous equations. Anyways, okay. All right, so now what I want to look at is I want to get into solving this system of equations. But that's sort of that's the background, that's the setup to what we're going to do. This is what big M is here, and we're going to define several other like parameters or numbers as well that's going to help us along the way. So we're first going to define M sub k. M sub k is going to be equal to M divided by mk. So like M1 is going to be equal to M1. Big M1 is going to be equal to little m1 times little m2 times little m3 over m1, which is just equal to m2 times m3. Okay, so that's what mk is going to be. It's like m, but without little m, little mk. Okay, and I've actually computed these. Big M1, let me try to write it like this. Big M1 is 2970. Big M2 is 2241. And big M3 is 9130. Okay, so here's another observation that I want to make, is notice that mk is congruent to 0 mod mj, and this is for j not equal to k. Okay, so in other words, m1 is equal to 0 mod m2. Big M1 is equal to 0 mod little m2. Big M1 is congruent to 0 mod little m2. And that's just because, what is M1? Well, big M1 is little m2 times little m3. In other words, it's a multiple of little m2. It's a multiple of little m3, so it's going to be congruent to 0. Okay. What we're going to do next, I kind of want to look, I want to look at each one of these m's, and I want to reduce them modulo little m. So I want to reduce big M1 modulo little m1. In other words, I want the remainder, not just something that's congruent to big M1, but I want the smallest congruency. Okay, and I'm going to define these in the following way. P1 is going to be equal to the smallest integer, M1, mod little m1. Obviously, m1 itself satisfies this equation, but I want the smallest one. And this, if I do P1 here is going to be equal to 65. In other words, 65 is the remainder of big M1 after division by little m1. So big 65 is the remainder of big M1 after we divide it by little m1. Okay, similarly, P2 is going to be equal to the smallest congruence here. And P2 is equal to 41. And then similarly, P3, we're going to reduce big M3 mod little m3, and we're going to call this P3, and it is equal to 4. So big P3 is equal to 4. Okay, so what we know then, big M1 is equal to 65 when we reduce by little m1. It's equal to 0 when we reduce by little m2. It's equal to 0 when we reduce by little m3. M2 is equal to 41 when we reduce by little m2. It's equal to 0 when we reduce by little m1. It's equal to 0 when we reduce by little m3. And finally, m3 is equal to 4 when we reduce by little m3, and it's equal to 0 when we reduce by little m2 or little m1. Okay, so we've got that information. We've got that with us. Now what we are going to do is we are going to solve the following recurrences. Actually, I need to point one thing out. These P1 and little m1 are relatively prime. P2 and little m2 are relatively prime. P3 and little m3 are relatively prime. And I want to explain why that is. Let's look at P1. I'm going to explain to you why P1 and little m1 are relatively prime. Okay, so I know that P1 minus big M1. Okay, they are congruent mod little m1. So this is equal to some number, some integer k times little m1. It's equal to k times little m1. Okay, now, sorry, my phone is dinging again. So now I can write P1. Actually, I'm going to change this around a little bit. M1 minus P1 is equal to K times little m1. Okay, K was allowed to, I would need to have it this way. K is allowed to be negative, but since m1 is greater than or equal to P1, we know it's going to be positive, but that's not important. Okay, then I can write m1 is equal to K m1 plus P1. Okay, now notice if we have a number that divides little m1 and P1, if we have a number D, if D divides m1 and P1, then it divides big M1. Okay, if I can factor out a D from here and factor out a D from there and have that be an integer, then it's also going to divide M1. Again, if D divides little M1 and big P1, it's also going to divide big M1. Okay, well, so then if we have a divisor D that divides little M1 and P1, it's going to divide big M1. In other words, it in particular divides little m1 and big M1. So in other words, it's a common divisor of little m1 and big M1. But the greatest common divisor of little m1 and big M1 is equal to 1. Okay, so the logic here goes, if we have a common divisor of little m1 and P1, it's also going to divide m1. So therefore, it's a common divisor of little m1 and big M1. So if you look at all the common divisors of P1 and M1, those are also going to be common divisors of M1 and little m1 and big M1, but there's only one common divisor of little m1 and big M1, and that's just equal to 1. So therefore, if you're a common divisor of little m1 and P1, you're a common divisor of little m1 and M1, that's only 1, so any common divisors of little m1 and P1 are just equal to 1. Okay, so the P's and the similar things are true for P2 and little m2 and P3 and little m3. Okay, and that's important because we're going to be solving equations like the following. We're going to solve P1 x1, we're going to solve P1 x1 is equal to 1 mod little m1. P2 x2 is equal to 1 mod little m2, and P3 x3 is equal to 1 mod little m3. Okay, in the previous video I showed exactly how we can solve equations like this. And we used in that video that little m1 and P1 had a GCD of 1. Okay, which is why I had to prove a second ago that the GCD of little m1 and P1 is 1, and so on and so forth. Okay, so when we solved this, I actually did this exact example. P2 is equal to 41. And little m2 is equal to 110. In one of the previous videos, I solved this exact example to get that little x2 is equal to 51. In the book, it solves this equation right here to get that little x1 is equal to 23. And then you can do it on your own to get that little x3 is equal to 7. So x1 is equal to 23. X2 is equal to 51. And then x3 is equal to 7. Okay. So then the solution, hold on. So then the solution to the differential, or not the differential equation, the system of equations is the following. Or this is a solution in, and then we're going to reduce it mod big M. So in is going to be equal to the sum k equals 1 to 3 rk times mk times xk, where this is rk, like this is r1, 32 is equal to r1, this is equal to r2, and this is equal to r3. Okay, now what I want to do is I want to show that this solution satisfies this equation here. Now, the basic way to think about this, I'm going to kind of give a brief explanation and then one that's slightly more detailed. If I take in, let's just think about this. If I take in and I reduce mod little m1 and reduce mod 83, okay, when k is equal to 2 or 3, big M is a multiple of m2 and m3. So when k is equal to 2 and 3, these terms are going to be 0 mod little m1, because big M2 and M3 are multiples of little m1. Okay, on the other hand, when I have R1 is equal to 1, or when k is equal to 1, big M1 is going to be congruent to P1 mod little m1, and then this is going to be congruent to R1 times P1 times X1, but P1 times X1 is 1, and then you multiply it by R1, you get, R1 mod little m1. Okay, that's a very brief explanation. A slightly less brief explanation is if I want to think about in mod, let me just write it like this, as mod 81, then this is going to be equal to R1 times big M1 times X1 mod M1 plus R2 times M2 times X2 mod M1 plus R3 M3 X3 mod M1. Now here, since M2 is a multiple of M1, since big M2 is a multiple of little m1, I know this is going to be 0 mod little m1. And since M3 is also a multiple, I know this is also going to be equal to 0 mod m1. Now m1 is equal to P1 mod m1, and P1 times x1 is equal to 1 mod m1. So then we're just left with R1 mod m1, and R1 is equal to 32. Okay, that's a slightly, if you're comfortable with modular arithmetic, that should be sufficient. But if you're not, I'm going to give something that's slightly more explicit here. That just basically explains this, but again, like I said, more explicitly. So what I want to do is I want to divide in by m1 and show that it's going to be equal to 32. So in divided by m1 is equal to R1 big M1 X1 over M1. So I'm not going to show it's equal to 32, I'm going to show the remainder is 32. Okay, plus R2 M2 X2 over little m1, and then plus R3 M3 X3 over little m1. Okay, so let's think about what the remainders are going to be. When I do this division right here, what's the remainder? Well, big M2 is equal to little m1 times little m3. So this the numerator is just a multiple of that. So the remainder here, there is no remainder, it's 0. And similarly here, m3 is equal to little m1 times little m2. So the numerator is an integer multiple of that. So, okay, there's no remainder there. So all we're left with is figuring out the remainder there. Or at least figuring out a congruence class of the remainder. Okay, so remember that M1, M1, big M1, and P1 are congruent mod little m1. Okay, so big M1 and big M1 and big M1 and P1 are congruent mod little m1. So in other words, what this means is P1 is equal to K M1 plus P1. And actually, this is the smallest congruence. Now, if I multiply both sides of this by big little r1 and x1, what I'm going to get over here is K times x1 r1 m1 plus K, plus r1 x1 p1. So in other words, what it tells me is that the remainder, when I do this division, the remainder that I'm going to get is going to be a multiple of r1 x1 p1, or they're going to have the same congruence class. So what this means is that r1 m1 x1 is going to be equal to r1 x1 p1 mod little m1. Okay, but x1 times p1, I went over this logic in the previous video. X1 times p1 is equal to 1 mod m1, so then this is equal to r1 mod m1. But r1 is just 32. And then similar arguments can be shown that n is congruent to 70 mod 110 and 3 mod 27. Okay. So, using the values of r1, x1, and p1 that I gave, and then plugging it in there, this gives that n is equal to 10,378,020. Okay, now remember capital M, I think I erased it. No, capital M is equal to 246,510. And what we want to do is we want to subtract off this number as many times as we can so that we still have a positive number. So I want the smallest, I'm going to subtract off this as many times as I can so that I still get a positive number. Okay, because if that's also going to be a solution. If I take this solution and reduce it mod m for the reasons that I discussed in the beginning of the video, that's also going to be a solution as well. Okay, so it turns out if we subtract off this number 42 times, we get what I'm going to call n naught, which is the smallest solution, which is well, I thought I had it written down in the presentation here that I'm using, but I don't. 24,600. And this is a solution to this system of congruences. Okay, and the problem that it came from, the final step is going to be divide this by 3, and that's how much rice each farmer had. Okay, so this is, like I said, the Chinese remainder theorem. We're looking at the specific case when all of the moduli are equal to m1. And then I think, again, I didn't put this in the board. I didn't put this as a list of the discussion posts. But another discussion post would be to, like, okay, give a general formula. If we've got, a system over here and moduli over here, give maybe some sort of general formula for what the solution to this, to that system of congruences would be. Anyways, I really like the Chinese remainder theorem. I think it's great, and I hope you guys enjoyed it as well.